Okay, so let me share screen. Yes. So, okay, great. Hi, everyone. So let me tell you one thing again, for those people who joined now, and also for the people who are watching on YouTube, let me tell you that this session, on exception, became online because my car got broken. Its battery died, so I couldn't go to Guelph today, but it got fixed fortunately fast. It wasn't, I didn't expect that it gets fixed fast, but it got fortunately now. So from the next session, the class will be in person again, not in Zoom. It will be in person again. I apologize for today that it became online. It was unexpected. Just yesterday night, I found out that its battery has died. And also, I have posted the solution to the assignment 1. And now, please, for the midterm exam, study the assignment 1 and its solution and the lectures. And as I had said, the exam is open book, but chatting and networking and ChatGPT and all of these are not allowed. The other things are allowed, and it's open book. And yeah, and also the exam will be in person. I will be in the class answering all of your questions and ambiguities. So, and so yeah, that's the thing. Any question? No? Was the assignment also clear? Yes. Okay. So let me start. So where were we stopped? We stopped last session on convolution or neural networks. We were in the middle of that. Let me continue with this. So we said that a problem with the feed-forward neural network is that when we have, for example, a 2D image or a tensor rather than a vector, then what happens? Then when we reshape it for feed-forward neural network, some of the spatial correlations are preserved, but some of them are ruined. For example, 2 and 4 are adjacent neighbors to 1, feature 1. However, when we reshape it, 2 is still the neighbor of 1, but 4 is not a neighbor of 1 anymore. And the larger the size of the image, the more disruption of this correlation we have. Also, if the tensor is 3D, we have a correlation in the third axis as well, right? And it will be ruined as well. So we said, by the way, feel free to interrupt me whenever you have any question. So what did we say? We said consider an image with its pixels as a data for the neural network, right? If the neural network is fully connected, it cannot capture the 2D spatial correlation of nearby pixels. We talked about it. This is because fully connected neural networks or multi-layer perceptrons, for them, we should reshape the input image to become a vector, right? Okay, therefore, convolutional neural network, or CNN, was proposed to get the images as they are and not reshape them. In this way, the neural network can consider the 2D correlation of pixels. Okay, then CNN, convolutional neural network, is a neural network which uses convolution in place of general matrix multiplication in at least one of its layers. You remember in fully connected neural network, we talked about it in the previous sessions, that every layer is like a linear projection followed by some nonlinear activation function. So we have U1 transpose X is input, then U1 transpose X is here, at the end of the first layer. Then we feed it to the activation function sigma 1. Then U2 transpose is applied as a second layer. Then we have the second activation function, and so on until the last layer, right? This was what we had in the fully connected neural network. But now, rather than U transpose X or general matrix multiplication, we use convolution in at least one of the layers. If we in the neural network, at least one of the layers has convolution, then it is convolutional neural network. So convolutional neural network might have some fully connected layers as well. And then we said CNN was initially proposed by Kunihiko Fukushima from Japan in 1980, and the network was named neocognition in that paper. So the idea of CNN then was adopted by Jan LeCun. I said Jan LeCun was in the University of New York. He's still there, and he's also the head of AI in Meta or Facebook. And at that time, he had a project on handwritten digit recognition. So he used that idea of CNN and developed that with the collaboration in collaboration with Yoshua Bengio, who is the godfather of AI in Quebec and Montreal, okay, nowadays. So they named the network after LeCun, who was the first author, I believe. So the network was called LeNet because of LeCun. LeCun starts with Lee and net for neural network, right? So this paper was the paper which proposed modified NIST or MNIST dataset too. That's why it has been cited a lot, because whoever uses MNIST in their paper, they cite this paper there also. So modified NIST and modified NIST, they were both datasets for handwritten digit dataset, such as 0 until 9, right? And it is a famous benchmark in machine learning nowadays for images. And the structure of LeNet was this. We talked about it briefly in the previous session. So we have the input, then we have convolution, and then we have a bunch of kernels, right? Kernel filters, and so as a result, we have a bunch of feature maps out of the convolution. So assume I have one filter I applied on the image, it gives me one of the feature maps. Then I have another filter, so I applied on the input, it gives me the other feature map. And I do it for several times. I have several feature maps which are separate. And then when I apply the convolution on the input, I will have a bunch of feature maps. And then we do the subsampling. We usually do subsampling nowadays by pooling. We will talk about it. We will talk about the details of this. And then they are downsampled. As you see, the feature maps get reduced in terms of size. Then we do the convolution again, subsampling again. We do it multiple times. Afterwards, we usually have several fully connected layers. And this is what they did. And now, until nowadays, we imitate them. And we usually, regular CNN networks have fully have convolutional layers at the start. At the end, they usually have fully connected layers. And I think it's obvious. Why do we need at least one fully connected layer at the end? Can you tell me? Can anyone tell me? No? The reason is that I need to make it reshaped to become the number of neurons at the end. Usually I do it for classification or regression, right? So the number of neurons should be the number of classes, for example, or the dimensionality of my label. As a result, I have to reshape it in the last layer. By the way, guys, please give me 1 second because I need to email everyone. Apparently, some people are joining the Zoom link in the other course. I am getting notifications here. Let me tell them that we are in this link. Just give me a second. Okay, so then yeah, this is the structure of LeNet that we discussed. And I also talked about briefly that why we have a convolutional filters in image processing, signal processing, right? And maybe in computer vision. And then I said, for example, there are some filters for edge detection, for smoothing and different things, right? And I gave you some examples in the previous session. Then I said some researchers said, why don't we learn the values of the filter kernel for our to be optimized for our own task? If we do that, then this is exactly what convolutional neural network does. I remember in my master's, I had the same idea, saying that why do we need to have fixed values in the filters when we are doing filtering on images, for example, or on signals? Your signal might be one-dimensional, then your kernel will be, filter kernel will be also one-dimensional. If it is an image, your filter kernel will be two-dimensional. But I'm saying that in image processing, in contrast to image processing where we have fixed values in the filters, let's learn them by optimization. This is exactly what convolutional neural network does. And that task might be classification, might be regression, etc. Right? Okay. So I think we stopped here in the previous session. Let's continue. Every convolutional layer has 3 stages. We have convolution stage, we have detector stage, also called activation function, and we have pooling stage. Let's talk about them. So do you remember I said that convolutional neural network has at least one convolutional layer? And now here I'm saying that a convolutional layer has 3 stages: convolution stage, detector stage, or activation function, and pooling stage. We talk about them one by one. Convolution stage. So as I said, recall filtering in image processing. We have various kernel filters for different tasks, such as edge detection, corner detection, smoothing, sharpening, right? And for example, for edge detection, we have Sobel edge detection, we have Prewitt edge detection. For corner detection, we have Harris corner detection. For those of you who are interested, you can Google them and read more about them. For smoothing, we have Gaussian filter. For sharpening, I think we have, as far as I remember, I think we have LOG or DOG filters as well. So, or Laplacian filters. Laplacian is kind of like second order derivative. We have these filters in image processing for doing these tasks. For example, here I'm saying that for these 2 filter kernels are Prewitt filter, proposed in 1970 to detect horizontal and vertical edges of the image. Consider these. So what does it do? These are ones, these are zeros, these are minus ones. Also here, these are ones, these are zeros, these are minus ones. Of course, this detects horizontal edges. I mean like this. And this detects vertical edges. I mean like this. Or this, doesn't matter, right? Here also can be like this. By this, I mean here is dark, here is bright. Okay, so these specific kernels are used for edge detection, feature extraction for edges. There are specific filters for specific tasks, feature extraction for specific tasks. But for general machine learning tasks, such as classification or regression, we may need to different filter kernels for feature extraction. By the way, you know that in neural networks, we are always extracting features, different features in different layers, right? So we are doing feature extraction. The kernel filters for various machine learning tasks and also a different data set, right? We need them. Even for the same task, we may need different filter kernels for different data sets. Do you agree? So for example, the task is still classification, but if we change the data set, the filters need to be changed according to the features of that data set. Maybe one data set is about nature images, images of the nature, but one data set might be images of animals or images of office objects, office equipment. Then these are different, right? Therefore, let us learn the best kernel values using optimization. And as I have always said, machine learning is all optimization for our task and our data set, right? This is the idea of convolutional layer. A convolutional layer considers the values of the filter kernel as learnable weights. So basically what we have as the values of the filter kernel, such as these become the weights of the convolutional layer, which are learnable by backpropagation, right? Which can be trained by the backpropagation algorithm. Okay. So convolution stage, the discrete convolution is defined as this. This is discrete convolution. If you have passed any course on signals and systems, for example, you might have seen this. So this is or any course on signal processing. So T here denotes the index or the time, A of T, and this is convolution at time T. So basically I have summation rather than integral because it's discrete, right? And I have XA WT minus A, right? So and by the way, you can see that this is A, this is minus A. So one of the signals is flipped in convolution. We often use convolution in more than one axis at a time for 2D image I. So consider image I. Let the kernel of 2D filter be denoted by K. Then the 2D convolution becomes this, Sij. Now I have I and J because it's 2D, right? I is the image and K is the filter kernel of filter. So I and J element, I throw Jth column. Then I have I M N and K, I minus M, J minus N. Summation is over M and N. Okay. As you see, again, one of the signals is flipped twice along x-axis and y-axis, right? So in other words, layer, by the way, the summation is over the number of rows and columns of the filter kernel. And here it's important. In the convolutional layer, we do not consider convolution in all range minus infinity to infinity, but only in the range of the kernel size. Do you see that? So basically, consider, for example, in image processing, when you have a Gaussian filter, in practice, our filter is limited, right? With some few number of cells like this. Right? For example, here is 4 by 4. But in theory, the Gaussian kernel goes until infinity, right? Like this. But in practice, we are limiting that filter to some strict values. Here, we are also doing that. We are filtering them to the number of rows and columns. We are restricting that. Okay, we can assume that the summations in convolution are in the all range minus infinity to infinity, but our signal is 0 after the size of the filter kernel. So basically, by this approximation, by this restriction, we are assuming that the filter is going is covering the whole range, but our signal is 0 around out of the range of the kernel, right? So we are making some assumption here. And also convolution flips one of the signals, as I said, such as the kernel filter. If it is 2D, we need two flippings, right? Usually, we do not flip the filter kernel in convolutional layer. Also in image processing, we don't flip that. Why? Because we are lazy. As we are usually lazy, we don't flip that. So we basically say that rather M and M, and we say M minus I, N minus J, rather than I minus M and J minus N. And I think it's obvious. It doesn't matter. It doesn't. This does not make any difference because if we flip the kernel, the network will learn the flipped weights of the kernel, right? If you don't flip it, it doesn't learn the flipped weights. So whatever you do, it will be absorbed in the back propagation. It will find out what to learn. If we do not flip it, the network will learn the non-flipped weights of the kernel. And these are the non-flipped weights. The non-flipped convolution is also called cross-correlation. And we usually use cross-correlation in both image processing and convolutional neural network. Okay. Okay. Now, compare a dense or fully connected layer and a convolutional layer. So this is fully connected, as you see. These are the neurons of the previous layer, the neurons of the next layer. They're all connected to each other, right? But convolutional layer, not all of them are connected to each other. For example, consider this as a filter kernel, and we are sweeping it over the input. The next time it will be here. The next time it will be here, right? Agree? So we don't have, let me clean this part again. As you see, compare these two. Compare these two. A convolutional layer is not fully connected. So the convolutional layer is a sparse, as you see, sparse, and not dense like fully connected layer. In a fully connected layer, every output neuron interacts with every input neuron. However, in a convolutional layer, there is a sparse connectivity, right? A sparse learnable weights. We don't have too many weights here, right? And we know that the sparsity is beneficial, right? Why? For betting on sparsity principle and Occam's razor. Let me tell you what I already told you, asked you to watch the video on overfitting and regularization. But if you haven't, let me recall you what I was said in that lecture. So betting on sparsity principle means that this is proposed by Hasty and Tipshurani at the Stanford University. It says that give me a dense version of the algorithm and a sparse version of the same algorithm, okay? And give me some data. Blindfold me without looking, then feed the data to both of these algorithms. Without looking, I will say that with high probability, I bet that the sparse algorithm works better. Usually, they have seen that empirically. They have seen that in the in experiments of machine learning that sparse algorithm works well. Also, you can justify that by Occam's razor. Occam was a logician and philosopher in an ancient time. He said that if two things explain the same phenomenon, the simpler explanation is the better explanation. I think it's obvious. An example is that I'm hungry. There are two explanations for that. Either I haven't eaten for several hours. This is one explanation. The other explanation is that an alien came, which was invisible, but it tricked me with some magic, and I got hungry suddenly. Both of these explain why I'm hungry, but which one is the valid one? Of course, the simpler explanation. Okay, so according to these two, we can say that the sparsity is a benefit of convolutional layer. Also being low rank, because when we are fully connected, we are not usually low rank. The weight matrix will probably have lower rank compared to a dense layer. And for rank is some rank of matrix. For more information, search it in linear algebra. Okay. As obvious in the above figure, this sparsity occurs because the kernel is usually smaller than the input size. Okay, do you agree that if the kernel is the kernel size is the size of the input, then so here kernel size is 2, right? These two. But if the kernel size is 4, then a convolutional layer is equivalent to fully connected layer, right? If the kernel size is the same size as the input, then it becomes a fully connected layer again. So if the number of input and output neurons of the layer are M and N, respectively, the runtime, the required space, and the number of parameters of a fully connected layer is of the order of M times N, right? This is big O notation. right? Because we have m neurons, n neurons, so we have m times n connections. That is why, but in the convolutional layer, assume kernel size is k, where k is much less than m. Okay, here, for example, k is 2, m is 4. Then the time complexity, the space complexity, and the number of parameters to learn in a convolutional layer is in the order of k times n, compared to m times n, and it's much less. Therefore, both time complexity and space complexity of a convolutional layer is better than a dense layer. Okay. There is another constraint in a convolutional layer, and that is parameter sharing. So the parameters, by the way, here in these slides, I'm telling you why convolution layer is working well. Nowadays, it's used a lot. I'm talking about the theory behind it. So that's parameter sharing. The parameters or weights of the kernels are shared. Do you see that? Consider this example where k is 2, kernel size is 2, and then m is 4, right? So here, this is one kernel, and then we sweep it. Then we have this. As you see, we are using the same weights. We are not using different weights between the across the sweeping of the kernel, right? So this is the same as this weight, is the same as this weight. Also, this is the same as this weight, the same as this weight. So we are sharing the parameters, right? In other words, we sweep the same kernel over the neurons in a convolutional layer. Okay. In a traditional, fully connected layer, every element of the weight matrix is multiplied by one element of the input. That is, it is used once when computing the output of layer. In a fully connected layer, we don't have parameter sharing, but we have it here, right? So in convolutional layer, every element of the kernel is used at every position of the input. That's also interesting, right? Every element of the kernel is used at every position of the input. Instead of learning a separate set of parameters for every position, we learn only one set. That's interesting. So we have a fewer number of parameters to learn. Another property of the convolutional layer is the equivalence property of the convolutional operator with respect to translation. So consider a function f of x. We say that it is equivalent to a function g of x if f of g of x equals g of f of x. In other words, if we illustrate it in this way, x is here, then we apply g on it, it gives us g of x here, right? Then we apply f on it, then this y becomes f of g of x, right? Now comes from the other side. X, apply f on it, it gives you f of x. Then you apply g on it, it gives you g of f of x. If these two are equal to each other, then we say that a function f is equivalent to a function g. By the way, for more information on this, you can see this is in the area of category theory in mathematics. Okay. So the convolution operator has equivalence property with respect to translation. And therefore, these two are equivalent. So I'm saying that here I told you what equivalence means. And now I'm saying that we have to consider f of x to be convolution operator and g of x to be translation, right? So these two, they are equivalent property with respect to each other. So in other words, when you translate image and then apply convolution, it is equivalent to applying convolution and then translating the image. Okay, and that's interesting. That's interesting. Note that convolution is not equivalent with respect to some other transformations, such as rotation and changes in a scale. It is equivalent with respect to translation. Okay. And important parameters in the convolutional stage. So we have some parameters such as stride, width, number of channels, padding. What are these? A stride is a step of jump of kernel in convolution. So we jump, for example, when this is our image, we convolve this filter, then we need to jump to the next position, right? The step of this jump is called a stride. Also, we need to jump in 2D, so in both axes, right? We go in one row and then we jump again to the next row. So we have a stride in both x-axis and y-axis. And if it is 3D tensor, rank 3 tensor, we have the stride in all 3 axes. So the step of jump of kernel in convolution. We have width, which is the width and height of kernel. We usually use the square kernels. And number of channels, the depth of the kernel. So do not confuse it with the number of channels of data or input and input of the filter kernel. So what do I mean by number of channels or the depth of the kernel? We might have several, we can consider it as several kernels rather than one kernel, right? And we call it number of channels. By the way, the input itself might have some channels. For example, if we have a 3D image with the channels of RGB, red, green, and blue, it has 3 channels. But I'm saying that the filters can, in each layer, we can have several kernels as well, right? Assuming my image has 3 channels, and my first layer, convolutional layer, has 4 filters. Then at the output, I will have how many things? I will have 3 times 4, 12 channels, right? Because 3 times 4, I have 4 kernels and I have 3 inputs, 3 channels of input. Okay, so that's one thing, number of channels, that's important. And padding, we can apply padding to increase the input width and height. Some padding methods are zero padding or mirror padding. What do I mean by these? So I mean when you apply convolution, we usually, for example, it is 3 by 3. We usually replace, when we apply the convolution, we usually replace the amount of the pixel by the result of the convolution, right? As you see here, these pixels are missed because we can't go outside of the image, right? For convolution. For considering these margin as well, not to miss them, what can we do? We can pad the figure to become a bit bigger so that we can also consider this margin. And how can we pad this? We can do zero padding by adding zeros here. Or we can have mirror padding. What do I mean? Just whatever pixel here I have, pixel value I have, I also put the pad to have the same value as its adjacent pixel. For example, here is 1, here I put 1. Here is 0.9, I put 0.9 here, right? So we have various ways of padding. Let's see some example of convolution with one channel of input. Let me just give me a sec. Let me bring this link. Okay, I need to stop sharing and share the screen. Do you see this? So here, as you see, we have done zero padding. And also the blue, the bright blue thing is the image. And my dark blue or dark purple is the kernel of the filter. And it is 3 by 3. So its width is 3 and my zero padding is 1 pixel, right? And also the number of channels is 1 because I have 1 filter. And also the number of channels of input is 1 because you can see it as a grayscale image, right? For example. And a stride here is what? Can you tell me? Stride is 1 because I move only 1 pixel to the right and bottom, right? So 1 pixel, 1 pixel when I go to the next convolution. If I jump 2 pixels, my stride would be 2. And consider the kernel filter is this. For example, in this iteration, this is my kernel filter, right? Assume. So these are the values at this current iteration of backpropagation, for example. And then what do I do? So I multiply at every convolution, I multiply the values of this kernel matrix by the values of the input. And then I replace the middle the middle of the kernel by the result of the convolution. Here are the calculation of the convolution, as you see below. And here we have the output matrix. And that is the reason we had zero padding, so we can also consider these values as well. Okay, now let's see an example of convolution with 3 channels. So, I mean, 3 channels of input. Do you see that? Consider these. So here, for each channel of the input, I'm using 1 channel of the filter. Therefore, it becomes like this. So here I'm considering my kernel filter is a cube, like a cube, and the result will be the result will be convolution of the whole cube with the input cube, and the result will be 1 pixel, right, as you see. And now can you tell me what it is doing? So here W1, W2, these are the 2 channels of the filter. So basically I'm using 2 cubes for filter. Once I have this, then the next cube, and these cubes of the filters have different values, and so on. Did you get it? So here, for example, here is our RGB, red, green, blue as input. Any question? No? So as you see, the first example was example of convolution with 1 channel of input. The second example was example of convolution with 3 channels of input and 2 channels of filter, W1 and W2. Agreed? Okay. So now we go to the next stage, detector stage. By the way, I think I'm just a hint for you guys to practice it. I think because it's easy and you can get easy mark on this, I will put 1 question about I guess I will put 1 question in the midterm exam about convolution. So I will give you some filter, some stride width padding, and then some input image, and then I said do convolution. And I think it's so easy for you to get mark. I just gave you a heads up that I want you to get good marks. That's why I gave you a heads up. Okay, detector stage. Detector stage is another name for activation function, another name. This is because they act like they detect the signal if the signal passes from some threshold. You remember, for activation function, we usually have some threshold, right? We already talked about activation functions before in this course, so I'm not going to repeat that. The same activation functions that we discussed can be used for convolutional layer as well. The next stage is pooling stage. Okay, in the pooling stage, pooling is performed. So pooling, what does it do? Pooling provides a summary statistics from the signal. So what do I mean by summary statistics? For example, mean is a summary statistics. Median is a summary statistics. These things that we learned in the statistics of high school, these are called because it summarizes the data, right? It provides a summary statistics. Some examples are max pooling. Maximum is also a summary statistic. Average pooling, weighted average pooling, median pooling, L2 norm pooling. So what do I mean? For example, consider this input, right? Max pooling with a stride 2 and width 2. Can you tell me what happens? So width 2, it means this. I consider this. for example. This is my kernel of max pooling. Then what is the maximum among these? Is 3, right? So I put 3 here. So I replace the whole thing with 1, the maximum of them. Then my stride is 2, so I should jump 2 pixels. If I jump 2 pixels, if I jump 1 pixel, it would be here, right? But I jump 2 pixels, so I will be here. Then what is the maximum of 7524? It's 7. Likewise, I jump 2 pixels down, so maximum of these is 8. And then I jump 2 pixels. What is the maximum between these? Is 6, right? Now let's see another example. Let me clean this part. So median pool with a stride 2 width 2. So median of these, let me write them down: 1, 2, 2, 3. So we know that when, as the result, they are even number of them, the median will be the mean of these two. 2 plus 2 over 2 is 2, right? Now this one, it's 2, 4, 5, 7. The median is 5 plus 4 plus 5 over 2 is 5. Did I write it correctly? 2, 4, 5, 7. The median is, I think, 4.5. I wrote it wrong. Sorry. Yeah. Okay. So these you can do median pooling. Also average pooling. What do I mean? With the same stride and width. Again, you have these values, you take the average, right? We can have weighted average. What do I mean? We can weight the pixels. So if, rather than using the same weight. If you use the same weight, it's simple average pooling. Otherwise, it will become weighted average pooling. So I talked about all of these. And L2 norm pooling, what do I mean? Consider this, for example, you can see it as a vector 2, 1, 2, 3. Then take the L2 norm of this. What is it? 2 to the, so square root of 2 squared, 1 squared, 2 squared plus 3 squared, right? Then it gives you a value. So you can summarize it in some way. And do you see that what it is doing? It's summarizing the input. As a result, it can be used for downsampling. Do you remember I told you that we can use pooling for downsampling? This is exactly what we are doing. So here, by the way, do you remember in fully connected layer, for example, we go from higher number of layers to lower number of higher number of neurons to lower number of neurons. Here we can, for doing the same thing in convolution layer, we can use pooling for downsampling. Okay. Now let's consider, so the parameters of pooling as stride, the step of jump for kernel of pooling, right? Based on a stride, pooling may be overlapping or non-overlapping. So we can have, if a stride is big, then we'll have the kernels will be non-overlapping. For example, when here a stride is, when a stride is 2 and width is 2, the pooling is non-overlapping, or it can be overlapping. Width is the width of the kernel of pooling. Usually we use square kernel for pooling. Number of channels is the depth of the kernel of pooling, which is the same as the number of channels in the input of the pooling stage. Okay. And padding, we can apply padding to increase the input width and height. So we can have padding for pooling as well. Some padding methods are, again, zero padding and mirror padding, as we discussed. Let's see some other examples. Consider this input. Max pooling with a stride 2 and width 2 is exactly what we talked about in the previous slide. Now, let's consider the example of max pooling with a stride 1 and width 2. So this is one thing. The maximum is 3. Then stride 1 goes like this, right? The maximum is 7. Then stride 1. The maximum is 7 again. As you see, we still have downsampled, but not too much because of stride. Stride, as it is overlapping pooling, then its size is bigger than stride 2. Okay. And another example is stride 1 and width 3. What do I mean? As you see, it's so simple That's why I'm gonna bring it in your exam so you get good mark. So width is 3. So maximum of these is 8, right? Then do one step stride like this. The maximum is 7, etc. Right? You can have 0 padding as like this too, and then do max pooling with a stride 2 and width 2 to get this. And you can play around with different ways to do pooling. So these are max pooling. You can have, as I said, different kinds of pooling. Pooling makes the features almost invariant to local translations. Okay. And so that's a benefit. So it has several benefits. One of the benefits of pooling is making it invariant to local translations, to small, slight translations. Because if we don't use pooling, then, for example, assume we learn this is 5. But if we have a slight change like this, the previous 5 was like this, for example. We will not find out that this is a new 5. Although we have a slight change, but the network will not find out that it was the same as the previous 5. But with pooling, we can get robust to these small changes, right? So, for example, and let me tell you why it is invariant to local translations. I can show it to you by one example. Consider the inputs. Okay, now I'm doing I think max pooling here with width 3, so we have 3, and stride 1. Okay, so what happens? So the maximum of these is 1, the maximum of these 3 is 1, the maximum of these 3 is 1, the maximum of these 3, for example, is 0.2. Okay, now let's shift the input a little bit to the right. Do you see? For example, this became here, this 1 became here, this 0.2 became here, and 0.1 went there, right? So I shifted that to 1 pixel to the right. Then what happens? Apply the max pooling again with a stride 1 and with 3. So we'll have 0.3, 1, 1, 1. How much change do I have? So here, all 4 features of input of pooling state have changed. Because of this shift, 1 pixel shift, all of the inputs have changed. Do you see that? 0.1 became 0.3, 1 became 0.1, 0.2 became 1, 0.1 became 0.2, right? Everything changed, but as you see, we don't have too much change at the result of the max pooling. So here 1 became 0.3, but 1 became 1. This 1 became 1. This 0.2 became 1. So only 2 features changed. Although 4 input features changed, only 2 features at the output of the max pooling changed. So now you can generalize it to bigger poolings. And if this is 1D, you can generalize it to 2D, and you can see that it is getting more robust to local translations. I showed this to you by some example. In most cases, it is good to become invariant and robust to local translations. But in some applications, maybe you don't, the local changes are important to you, and you don't want to become invariant to them. And if you become invariant to them, it is destructive. But usually, it is helpful because we usually want to know whether a specific feature exists in the data, but we do not care where exactly it is. For example, we have digit 5. We don't care whether it's here or here, right? As a result, pooling is usually helpful. Okay. Now, pooling, also another benefit of pooling is downsampling. So this reduces the representation size and hence computational and the statistical burden on the next layer, because we want to make it smaller and smaller. So as you see, for example, here in this example, a stride is 3 and width is also 3 for pooling. And as you see, 1, 2, 3, 4, 5, 6 features became 3 features, smaller, downsampled, right? Any question? No? Okay. we can see both convolution and pooling stages as infinitely strong priors. What do I mean? Again, the theory behind pooling. So consider this is weak constraint, weak prior. So you can, this is a distribution, right? Some distribution. You can make this distribution stronger. By the way, prior means prior probability, right? You can have a stronger prior like this, right? By reducing the standard deviation. You can then, however, here you still have small probability, which are not zero. You can make them completely zero like this. So here, these are completely zero, right? Set some weights to zero. This is exactly what we are doing in pooling. We are setting all of these to zero, and we are taking only some of them. This is called infinitely strong prior, right? Again, as you see, because of putting these to zero, it is like betting on the sparsity principle. It is sparse, so it's good for betting on sparsity principle and Occam's razor that we discussed. Okay. Now, also, we can dynamically pool the features together rather than pooling the neighbor features together only. So one might ask, in pooling, we are only pooling the adjacent features, right? Or adjacent pixels together. For example, we are applying max on the adjacent pixels. One might say, who says that getting the summary statistics of the adjacent features is good? What if we maybe some features from here and some features from there, if we take the summary statistics of them, it's more beneficial for our task of classification or regression. Who knows that? Let's find it out. Let's find it out. So we can make it dynamic pooling. For example, we can run a clustering algorithm such as k-means on the locations of interesting features, right? Then we can pool the features in the same cluster. You can see reference 10 for that. So we can cluster the input at every layer, or input of every layer. So of course, the input of the first layer is the input data, the image, right? Then at every layer we have input. So we can apply k-means on the features. Then we can find out which features are closely related to each other. And then we apply pooling on them. That's interesting, right? In this way, different sets of pooling regions will be used for different data inputs. And do you see that? Because every input which comes, every input image which comes will have different clusters. So per data, our pooling will change. That's interesting, per data instance. We can rather learn a single pooling structure, and then we apply that learned pooling structure to all data inputs. So rather than having a different pooling per data instance, we can learn a single pooling structure and then use it for all of the data inputs. You can see reference 11 for that. Okay. Then we can use pooling to handle inputs for varying size as well. So another benefit of pooling, as I'm enumerating different benefits of pooling here. One of the benefits is handling different sizes of image. For example, because this is a problem for convolutional neural network, right? Because it needs to accept images with the same size. One technique to handle that, there are several ways to do that. One technique is that using pooling. So for example, we have big image and we have a small image. Then we use pooling on them to become the same size. If we set the width of the pooling kernel according to the input size. For example, if it is too big, then get the large width for the pooling. So this is summary statistics of this. This is summary statistics of this. This becomes this. This becomes this. Now, if it is a small image, the width of the pooling is small. This becomes this. This becomes this. This becomes this, and this becomes this. As you see, these two have the same size. Interesting, right? So you can handle the varying sizes of the input. Any question? No? Batch normalization. This batch normalization that I'm talking here can be used for fully connected layer as well. not just for convolutional layer. That's a regularization technique. Okay. Batch normalization was proposed in year 2015. What does it do? It can be used in various network structures, including fully connected and convolutional layers. So it helps prevent covariate shift. Covariate here, the data, you can see it as covariate. Usually, if you have data X and the labels Y, you can see X or data X, they also call it covariate in the statistics, okay? What do I mean by covariate shift? You can see it as the domain shift. For example, what if your batches, so you are training by batches, right? You have training batches, you have test batches. Even between the training batches, you might have some domain shift. For example, this batch might have a Gaussian distribution, but the other batch, its distribution might not be Gaussian. Or in other words, in another case, they both might be Gaussian, but one of them might have mean 0, the other one might have mean 0.1. Or the standard deviations might change. So the different batches might have different distributions or different parameters of the distributions. Even between the batches of the training, the batches of test also might have difference. So for handling these shifts of batches, and as you see, it confuses the network what to do. In this batch, you say, learn this batch, and in the next batch, the network sees that it is completely different. For example, you're training a human, you're training a human to speak English, for example. In one batch, you tell that person, okay, this sentence, this word means this word means this, and in the next batch, suddenly you switch to German. You teach German. Then in the next batch, suddenly you go back to English. Then in the next batch, you go to Japanese, for example. That person gets confused. You need to remove these domain shifts or coverage shifts. And if for removing this coverage shift, we can use batch normalization. It helps also generalization and avoiding overfitting, okay? That's one of the regularization techniques. It helps trainings to be faster. Also, we have seen that it makes it faster for training because it doesn't confuse the network. Assume the input of a layer is X, d-dimensional. So the layer has D neurons, okay? Then for a mini batch, let the input of the layer be a set x1 to xb. So the batch. B is the batch size, okay? Let xij denote the jth dimension of xi. So xi is xi1 to xid, okay? Then batch normalization standardizes or applies z-score normalization on every feature. I don't know if you have heard of standardization, also called z-score normalization. What does it do? It says you have a bunch of data points, right? Then you make the mean 0 by this standardization and the standard deviation 1. So the distribution becomes a standard normal distribution or standard Gaussian distribution. And in batch normalization, we do this transformation for every feature, for every neuron's inputs, okay, over the mini batch. Consider this. What is this? This is the mean for the jth, mean for the jth feature. You see that? And as xij is a scalar, this mean is also a scalar. And the mean is over the batch. Also, we have a standard deviation, or so here it is variance. Variance over the batch, xij for the jth feature, minus mu j, which we calculated here. And it is a scalar, right? Because its feature is a scalar. And then this is the transformation that we talked about. Xij minus mu j over the standard deviation. So a standard deviation is square root of the variance, right? However, what if the variance becomes too small? For not having division by 0 or for stability, we add variance with we add it to some small positive value, very small, right? For stability and prevention of possible division by 0. What does it do? The mean becomes 0 and the standard deviation becomes 1. So that feature, the batch along that every feature becomes like a standard Gaussian distribution. And as you see, we removed the coverage shift. We made them all to become standard normal. And then we feed it to the next layer. Okay. Any question? Okay, initialization of kernel layer weights. So backpropagation is a gradient descent and chain rule. Do you remember in derivatives? We talked about it. So we need to initialize the weights. Do you agree? Or the optimization variables for backpropagation, because it is an iterative optimization problem. We need to initialize. Two ways to do initialization. One way is, I think, is most of you guys do, is initialization by random features, right? So it is randomly you set the features to be some values, and you can use either uniform distribution or Gaussian distribution for generating random features, random weights. And you can do this for both fully connected layers and convolutional layers. And it is related to random projection and Johnson-Lindruss lemma. What is that? Let me tell you briefly. Do I have it here? Yes. So this initialization by random features. It is related to random projection and JL lemma. JL lemma is short for Johnson-Lindruss lemma. I have a tutorial paper on that. Feel free to see that. It's reference 14. Okay. So basically, what does it say? It's very interesting. Let me show you. I think I have it. Just give me a second. So this is a tutorial paper. You see that, right? Okay. So do you remember we talked about linear projection, right? And in linear projection in machine learning, we have some projection matrix. This is linear projection, U transpose X, do you remember? And U is the projection matrix. And what does U transpose X do? It projects X onto the column space of U, okay? And recall preliminaries, we talked about these in preliminaries. And but in machine learning, we usually learn this matrix U, right? For example, in PCA, we learn this matrix U by optimization. Or in Fisher discriminant analysis, we learn this. For seeing some of these algorithms for learning U, see my statistical machine learning course, okay? And also I said that fully connected layer can be seen in neural network, can be seen as a linear projection, right? But random projection is very interesting. It says, don't bother learning U. Just let them be random, and with some like Gaussian random, okay? So randomly set the elements of the matrix U, and you can see that it works very well. For example, what do I mean? For example, you have some data classes in X, right? This is your data set, right? It has some classes. Then when you project onto the column space of U, where U is random, it is still separates the classes well enough. That's shocking, right? You are not learning anything for U. It's random, but it is working well. And it has some proof. For proof, you can see my tutorial paper here. The proof is long, like this, several pages, okay? The proof is for, so the proof is called Johnson-Lindruss lemma, JL lemma. What does it say? It says that, let's read it together. For any set X, so these are the data points, X1 to Xn, and integer n is the sample size, right? Epsilon is between 0 and 1, is the error tolerance, okay? Let P be the positive integer satisfying. So P is the dimensionality of the column space of U. Do you remember? Recall preliminaries. U transpose X projects X onto the column space of U, and if we have P columns, it projects X, which is D-dimensional, onto a P-dimensional subspace, where P is less than D. Do you remember? In the preliminaries, we talked about. Okay, so now P is a positive integer number satisfying this. So it says that let P, or the number of columns of U, satisfy equation 18. So omega is, it's big omega is, you know, big omega is the lower bound in the complexity. We have big O notation, big omega notation. This is lower bound. Big O notation is upper bound. Okay, natural logarithm of n over epsilon squared minus epsilon cubed. Okay, P must be greater than this. Okay, now or this equation 19. So two ways to have this JL lemma. Then there exists a linear map F, which maps from RD to RP, because this linear projection, do you remember, it projects the d-dimensional data to the p-dimensional subspace, right? X, it projects it onto U transpose X, right? Onto the column space of U, where U is a projection matrix and it is D by P, right? Okay, this now equation 20. So this, we have it. Yeah. So here, then we says that we have this. What does it say? Can you tell me? Let's talk about this. Equation 20. What does it say? F of xi means that linear projection of xi onto the column space of U. F of xj means linear projection of xj onto the column space of U. Basically, F of xi is U transpose xi. F of xj is U transpose xj. Okay. What does this mean? Which I highlighted. This is a norm of F of xi minus F of xj. This basically means that after linear projection, what is the distance, the squared Euclidean distance between xi and xj after linear projection? Okay. Now, what is this? Which I highlighted. The squared L2 norm of xi and xj. This is Euclidean distance before projection. Euclidean distance of xi and xj before projection. Also, we have it here too. So on both sides of inequality. However, in the left-hand side, this distance is multiplied by 1 minus epsilon. And on the right-hand side, it's multiplied by 1 plus epsilon. And epsilon is a small positive number, right? So basically, what does it mean? If we don't have these 1 minus epsilon and 1 plus epsilon, what does it mean? It says that the distance between xi and xj after linear projection is sandwiched between the distance before distance of xi and xj before linear projection. So if we don't have 1 plus epsilon and 1 minus epsilon, this distance will become equal to this distance. The distance before projection becomes equal to distance before projection. Do you know? I think you understand why. Because it's sandwiched between the same values. For example, consider the middle case is Benjamin. This squared Euclidean distance before projection, consider it to become table. So Benjamin is sandwiched between table and table. As a result, Benjamin equals table, right? But here I have 1 minus epsilon or 1 plus epsilon. Basically, it says that Benjamin is sandwiched between 1 minus epsilon times table and 1 plus epsilon times table. And epsilon is a small number. It's still sandwiched, and the sandwich is tight because epsilon is a small positive number, right? So basically, in simple words, Benjamin is tight, is in a tight sandwich between tables, right? Table. Going back to mathematics, it's saying that the Euclidean distance before projection, the Euclidean distance after projection is sandwiched between a scale of Euclidean distance before projection. So basically, the Euclidean distance is preserved almost with the error epsilon after projection. It's very interesting. So it's, in simple words, it says that I'm projecting onto a random column space, but the distances of points have been preserved with a small error epsilon. Did you get it? And it has a solid proof. And it was shocking when it was proposed. It says, why are you learning this matrix U? It's working well even if you do it randomly. Although it's not perfect. Of course, if you learn it by optimization such as PCA, it becomes better. It's not perfect, but it has some level of optimality in it. Did you get it? This is called random projection. Now let's go back to the slides. So I was talking about this, right? According to the JL lemma, as I said, you for proof, see my tutorial. If we set the layers of the neural network randomly initially, even initially it is working well. That's why when you have initial random initialization, it is still working almost well, but we make it better and better by optimizing and tuning that. But it is a good initialization because of the random projection and Johnson JL lemma. Recall that I told you that every layer of neural network is like a linear projection. And when you set the linear projection, the way it's random, it becomes a random linear projection, right? So the values also should not be too large, not to have gradient explosion, right? They also should not be too small to have gradient vanishing, because if they are too small, then in the chain rule, we have the small values, we'll have great vanishing. If it is too large, then we'll have gradient explosion. We have multiplication of large values. So here again, I have talked about linear random projection. I already talked to you about this. So by the way, the U transpose X is a linear projection. You can also scale it by 1 over square root of P, where P is the dimensionality of the column space. Okay. So yeah, in contrast to other linear dimensionality reduction methods, which learn the projection matrix using training data set for better representation of class discrimination, random projection does not learn the projection matrix, but randomly samples it independent of data. Surprisingly, it is working well because of JL lemma. Justifies that. For more information, see our tutorial paper. Another method for, yeah, also here I have brought the JL lemma in the slides, but we already went through that, right? And another method for initialization of the weights is this, which I skipped, is learning the weights by an unsupervised method. We can learn them by, for example, principal component analysis, PCA. For more information on PCA, see my statistical machine learning course. Basically, what is it? If you don't know what PCA does, it finds the most variant directions of data. For example, if I have this cloud of data points in 2D, the PCA learns these two, because my cloud has the most variant direction in this direction. Also, my second variant direction is this, right? So if I use all of the directions of PCA, it's just a simple rotation. As I see, I'm rotating these axes to these. But if I use a few number of principal directions, for example, I drop this, then it becomes dimensionality reduction. So the whole thing becomes a line like this, right? So we can use principal component analysis, which is an unsupervised method. We don't use labels for that, for the weights, for initialization of weights. What do I mean? I have explained the details here. Divide the input of the layer into some patches, right? You can divide it into some non-overlapping patches, or overlapping, doesn't matter. I think here it needs to be non-overlapping. The patch size S can be the stride of the kernel for convolution. For example, this is my kernel, then I have the some stride, right? Then assume my stride is 1, then I set the patch sizes to be 1 by 1. If the stride is 2, then I set the patch sizes to be 2 by 2. You get my point, right? Then shift the patches a little bit by some features or pixels. Okay, so I have some patches, then I shift them a little bit. Okay, then collect all the patches before and after shifting, okay, and reshape them to become columnist vectors. So basically, what do I mean? I have divided it into several patches, then I shift these patches a little bit, like to become like this. Every patch I reshape it to become a vector. Then I will collect all of these vectors together to become like a data set, right? Then I can apply PCA on these data vectors, right? On the patches. What does it do? It gives you S by S eigenvector matrices. For more information on how PCA works, see my statistical machine learning course. But if you apply PCA, then you will have S by S eigenvector matrices, okay? Then for the covariance matrix of that. Why? Because every data is S-dimensional here. Every vector here is S-dimensional. Then make a matrix with the size of the input where the S by S eigenvector matrices of PCA replace the patches in the big matrix. So here, basically put these S by S matrices next to each other again. It gives you the whole input weights again. This matrix can be the initial kernel of the convolution of that layer. Why do we do that? What is the philosophy behind that? By doing this, first off, we are learning the most variant directions of the data. So we are initializing the weights by the most variant directions of the data. And it is unsupervised, right? We didn't use labels. Also, we became robust to small shifts. This is a small shift, right? We became robust to this shift. Yeah. So, and do this for all layers to find the initial kernels for every layer. Interesting. So this is another way, but it is not used a lot. Usually we initialize the weights by random initialization. By the way, there was a third way to initialize the weights, and that was using the restricted Boltzmann machine. I have talked about it before in this course. So you can consider every two layers of the neural network as one restricted Boltzmann machine. So the whole neural network, you can see it as a deep belief network or a stack of RBM, restricted Boltzmann machines, right? Then I said we can use some training, energy-based training, to tune these parameters. If we have time in this semester, I will probably go over RBM, or I might cover some other important topics in the course. I should see how the course goes on. Anyways, so we can use RBM training for initialization of the weights too. Basically, actually, it was used for initialization of weights until the year 2011. But at that time, ReLU and dropout were proposed, and they saw that when they use ReLU and dropout as a regularization techniques, they can initialize the weights randomly and they become deep. Because before that, when they initialize the weights randomly, they would face gradient vanishing or gradient explosion, and they couldn't make the networks big, deep. Therefore, Hinton proposed RBM training. But later, because of ReLU and dropout, they found out that there is no need to do initialization by RBM, so they did it by random initializations. Nowadays, as a result, we are using random initialization, and I told you why it is working according to the random projection. Any question? No? Okay. Acknowledgement. Some slides of this slide deck are inspired by teachings of Professor Ali Qudsi at the University of Waterloo Department of Statistics. And these are the references. Okay, before we start the break, let me tell you, because there are more people now in the class, that this session was online because of my car got broke and I couldn't come to Guelph. But my car fortunately got fixed today, surprisingly fast. So now, from now on, the next session will be in person. Please come to the class from the next session. Also, the exam will be in person. So this session, on exception, was online because of emergency. But from the next session, it will be in person. Also, for those of you who have a statistical machine learning, the session, the upcoming session will be in person. I will send an email for that. Thank you very much. Any question before we start the break? No? Okay, let's have a break and come back at maybe 8:45. Is that good? Okay, guys, let's continue. Uh, yeah, so now we are gonna cover important convolutional neural networks. So there exists, so in the previous slide deck, we talked about the convolutional network itself. Now we have variants of convolutional neural networks, and we are gonna cover them. There exists various convolutional neural networks. Some of the most important and well-known ones are listed below. So what are they? One of them is AlexNet, proposed in 2010, reference 1. The other one is VGG in 2014. The other one is Inception and GoogleNet in 2015. UNet in 2015, ResNet in 2016, DenseNet in 2017. By the way, AlexNet, which was proposed in 2010, it was published in 2017, but it competed the ImageNet large scale visual recognition challenge, which we'll talk about, in 2010. Okay. Most of these neural networks were developed by big companies, and they often were winning the ImageNet large scale visual recognition challenge, or ILSVRC, in different years. So why are they important? First off, they were developed by big companies such as Google, Facebook, etc. Also, they were winning a very hard, challenging competition named ImageNet Large Scale Visual Recognition Challenge in different years. Yeah, and what is that? This is an annual classification challenge in machine learning and image processing, because its data set is image data set. ImageNet, so let's talk about ImageNet and that competition. ImageNet is an image dataset, so don't be confused with a net in it. It's not a neural network. ImageNet is a dataset of image, okay, containing 15 million labeled high-resolution images with about 22,000 classes, okay. And the images of the ImageNet were collected from the web and manually labeled by humans using Amazon's Mechanical Turk crowdsourcing tool. So there are some tools that humans can label the images. They use that Amazon's tool for manually labeling them. Since 2010, ImageNet, a large-scale visual recognition challenge, or ILSVRC, has been held as a part of the Pascal Visual Object Challenge. Okay. This ILSVRC is an annual classification challenge in machine learning and image processing. The data set in so every competition has some data set, right? The data set in this competition is a subset of the ImageNet, not the whole image. It's a subset of the ImageNet with 1,000 classes, each of which having 1,000 images. So each class has 1,000 images. So in total, it will be, I think, 1 million, right? 1 million images. And so now imagine how big the ImageNet itself is. ILSVRC dataset, so the dataset that I talked about, has about 1.2 million highest resolution images with 1,000 classes. The images are 224 pixels by 224 pixels. So they are square images with 3 channels of RGB, red, green, blue. Okay. 1,000 classes. Okay, now let's talk about AlexNet, the first variant of the convolutional neural network. By the way, AlexNet was proposed by someone named Alex. So let me tell you a bit of its history. So hence the name AlexNet. It was named after Alex, and Alex, I think, was a student. I believe he was a PhD student or a master's student. I don't remember. A PhD student under Hinton, Jeffrey Hinton, who was one of the godfathers of AI. Backpropagation, one of its proposers, one of its contributors is Hinton. So Alex was his student, and under his supervision, and he worked on some neural network. Hinton told him, do this, and he tried different architectures, and using the guiding of Hinton, finally he came up with some neural network which worked very well, and they named it AlexNet. So he wanted to use that neural network for the competition that I talked about, and he won. And the second rank was much below that. For example, I don't remember, assuming that AlexNet got 60% accuracy, the second rank was maybe 30% or 40%. So the gap between the first rank and the second rank was high. So AlexNet won, and because of the AlexNet, people found out that neural networks are very powerful, very powerful. So what does it have? It has 8 layers. The first 5 convolutional layers, and then 3 fully connected layers. Do you see? It's inspired by the LeNet. LeNet was similar structure, right? And the network of AlexNet is spread into 2 GPUs because it was too big to fit in the 3 GB memory of 1 GPU. At that time, his machine had each GPU of his machine had 3 GB memory, and he couldn't fit everything in 1 GPU. So he split that into 2 parts and spread into 2 GPUs. This also accelerates the training phase because it parallelizes that, right? The settings of the layers are like this. Layer 1 filters are 24 by 224 by 3. It takes them, so the input images have 224 by 224 pixels with 3 channels RGB. It takes them, right? With 96 kernels. What do I mean? The number of channels of the number of filter channels in the first layer is 96, right? With size 11 by 11 by 3, right? And with a stride 4, okay? Then layer 2 gets the 11 by 11 by 3 feature maps, which were generated by layer 1, output of layer 1, with 256 kernels of size 5 by 5 by 48. Then layer 3 gets the 5 by 5 by 48 feature maps, which were the outputs of the layer 2, right? Then it has 384 kernels of size 3 by 3 by 256. As you see, it's reducing the kernel sizes. Also, I think for understanding every algorithm, put yourself in the shoes of the designer of the algorithm. Assume you are Alex. Now you can understand how he was developing this. I think in the first day, he worked on layer 1 and layer 2 maybe, then went to Hinton and said, Hinton, professor, it's working very well. Hinton says, okay, add another layer and see how it works. I think it was, if we were in the meetings of them, I think this was the conversation between them. So they after every meeting, Alex added 1 layer to see what happens. So he was adding layers and layers. So layer 4 filters 3 by 3 by 256 feature maps, output of the layer 3 with 384 kernels of size 3 by 3 by 192. As you see, these 2 layers are very similar, but these are different. The number of channels are different. Also, he added 3 by layer 5, which takes the 3 by 3 by 192 feature maps, output of layer 4 with now how many kernels? The number of channels, 256 of size 3 by 3 by 92. So he was adding until it works very well. Then also he added layers 6 and 7, which were fully connected, inspired by LeNet. And they have in total 496 neurons. Of course, he made the neural network big. So for this to be learned, trained very well, the data should also be big. And we know that the dataset of ImageNet dataset is very big too. So it's working very well. The last layer is a fully connected layer with 100 neurons. Can you tell me why? We need one last layer to with 100 neurons, because we want to do classification where we have 1000 classes, and each neuron should correspond to one of the labels, one of the class labels. And for example, we can use cross entropy or some kind of loss for training, right? I think they didn't use cross entropy as far as I remember, but you can use, nowadays we usually use cross entropy for classification. Okay, all layers except the last layer have a ReLU activation function. As you see, at that time they found out that the ReLU is working very well, so they used ReLU for all layers except the last layer. Nowadays people usually do that a lot, so since then we do that a lot. We usually put ReLU in the hidden layers except the last layer. Can you tell me why? Again, it's a good regularization technique. It has worked very well in practice. It makes the data sparse. So it's good according to betting on a sparsity principle and Occam's razor. So it has a lot of benefits. And also it avoids overfitting and gradient vanishing and explosion as well. So this ReLU, and they also saw that by experiments, the ReLU accelerates training. It's interesting, similar to acceleration of training by batch normalization. ReLU also accelerates training and has been found to be effective. Okay, then the last layer has 1000 neurons with softmax activation function for classification into 1000 classes. Why do we use softmax? To recall the lecture that we talked about activation functions. Softmax makes it like probability distribution where they all sum to 1 and they are between 0 and 1. So we will have probabilities of the belonging to classes, and the bigger the probability, the maximum probability shows the estimated class label for that data, input data, right? So in the layer 1 and layer 2, a local response normalization was applied after the ReLU activation function. So this that I'm talking about, local response normalization, was used in AlexNet, but nowadays it's not used. So some things were used in AlexNet that we use nowadays, such as ReLU, but some things were dropped in the literature gradually. They found out that it's not useful or it's not needed anymore. He used local response normalization, and it was applied after the ReLU activation function. So it was empirically found to help generalization in AlexNet. Let A, X, Y, I denote the output of the kernel I, because we have several channels, right? Consider the ith channel. At the position X, Y, followed by ReLU activation function. So A, X, I, Y, then we feed it to the ReLU activation function, right? No, sorry. Yeah. So it has the activation function in it too. Then the local response normalization is this. Basically, this is after the ReLU activation function. Okay. Then we do this, and this is called local response normalization. What does it do? As you see, it's normalizing this AI, X, I, Y. So what is it doing? So I think I have explained this here. The summation here is over the n adjacent kernel maps at the same spatial position, and n, big capital N, is the total number of kernels in the layer. So n is a number of channels in the layer, how many kernels we have, okay? Capital N. And what does it do? So basically it says that summation over n adjacent kernels. What do I mean? Assume I have 5 kernels, capital N is 5, and assume my small n is 2. So how should I say? So this is one channel, one channel, one channel, one channel, one. So I have 5 channels. Assume I'm here. My I is 1, 2, 3, 4. Okay. Then if my n is 2, then it considers n adjacent kernel maps. So 2 adjacent kernel maps, these 2, right? Do you see that? So this basically means that consider the adjacent maps so that you will consider n adjacent maps. Then, this summation is over n adjacent maps, and it takes AXII for all of the n adjacent maps. Then alpha here is a hyperparameter. Beta is also a hyperparameter. Beta is a power. K also is for avoiding division by 0, right? It's hyperparameter and determined by validation, right? Alex found that K is good to be 2, N to be 5, alpha 10 to the power of -4, and beta to be 0.75. Okay. So as I said, nowadays we don't use this anymore, but Alex found it to be useful for his network. Then there is max pooling after layer 1, layer 2, and layer 5. Do you remember we talked about the layers in the previous slide? Now, after layer 1, layer 2, and layer 5, he used max pooling for, of course, for downsampling and all of the benefits that we talked about. In layers 1 and 2, the pooling is applied after the local response normalization. Okay, do you remember? For layer 1 and 2, we have local response normalization, which was after the ReLU activation function. Then after the local response normalization, we use max pooling. For layer 5, we don't have any local response normalization. The width of the pooling kernel is 3, and the stride is 2. Therefore, it uses overlapping pooling. Okay. Then AlexNet has 60 million parameters. Do you see how many parameters or how many weights it has? 60 million. And 650,000 neurons. Too many neurons, right? So these are weights and these are number of neurons. In the competition of the year 2010, it achieved the top 1 and top 5 error rates of these. What do I mean by top 1? So we can always consider the nearest neighbor for classification. We can also consider the 5 nearest neighbor classification, right? So top 1, of course, I think is harder. That's why its error rate is larger, and top 5 is easier, so its error rate was smaller. But again, top 5 and top 1, these error rates are very good. Sorry, let me reshare. Sorry, just give me a second. My device. Okay. So yeah, I was saying. So top 1, as you see, these errors are not much, and it was very good at that time. AlexNet was named after Alex Krichevsky, the main co-author of AlexNet paper. By the way, he has a good I read somewhere that he went to industry, but after some time he got tired of neural networks and he quit his job. I read that somewhere. That was interesting. Sometimes people get tired of what they are doing. So this is AlexNet. Credit of image is for his paper. So consider this is the image, right? And as I said, it is spread into 2 GPUs. So top is GPU 1 and below is GPU 2, right? As here it is divided into 2 parts, right? And these 2 parts are repeated. I mean, their structures are repeated. And so as you see, we have, these are the channels of layer 1, channels of layer 2, channels of layer 3, etc. And we have also max pooling here, here, and here. And then we have some dense layers here, right? And these are, finally, we have 1,000 neurons at the last layer for the classification. Do you see that? Okay. The loss function of AlexNet is maximization of the multinomial logistic regression. So do you remember I talked about logistic regression in this course, but logistic regression was for I think binary classification. We can have it for multiple classification, and that's called multinomial logistic regression. But anyways, so basically they are maximizing the logistic regression. They want to maximize the probability for belonging to the correct classes, right? And I think, you know, we need to minimize, because so this is the probability of why I been in the class L correctly. This is the logistic function, right? And as you see, I have summation over 1,000 neurons, because I'm using softmax activation function in the last layer. Then I'm maximizing that, but we know that in neural network we usually minimize that, so we minimize minus that, right? So this is what they are doing, and OJ here denotes the jth output of the network before the softmax activation function. Okay, this is softmax, right? This is softmax activation function. Recall that lecture we talked about activation functions. AlexNet is over. The next important architecture is VGG. By the way, we are going in the history. So after AlexNet, VGG was proposed. VGG, neural network, was proposed by a team named Visual Geometry Group. So the name of neural network is not related to the neural network. It's because it's named after the team, the name of the team. The team was Visual Geometry Group at the University of Oxford. Okay. So VGG addresses the depth of the neural network. So what does it say? It increased the depth of the neural network to a very long depth in order to have more learnable parameters to handle the nonlinear patterns of data better. So basically, now put your shoes in at that time in the shoes of the people at that time. So people saw that now they can make the neural networks deeper and deeper because of the ReLU activation function and regularization techniques. Even with random initialization, they can make it deep without having the problem of gradient vanishing and explosion. So they said, why not make it too deep? Let's make it as deep as possible. And they knew that they were, can you guess why they could do that? Because they were Visual Geometry Group. They were working on graphics, right? So they had a lot of GPUs. So they had a lot of resources. They said, let's use them to make the neural networks very deep, because we are a graphics group and we have a lot of GPUs available. So of course, they increase the depth, but when they increase it, they increase the learnable parameters. They must use a big training data. Otherwise, we'll have the problem of overfitting, right? So they also use a big data. For increasing the depth of the neural network, it added many convolutional layers. In other words, VGG can be considered as a convolutional neural network with too many convolutional layers. Too many, okay? So they were eager to increase it as much as possible. Like some person who is hungry and is eating as much as he or she can, right? So VGG uses very small convolutional filter kernels with size 3 by 3. So they decrease, of course, if they increase the depth, but with a regular width of the filter kernels, they will have too many weights, and but they don't have enough data to train them. Therefore, for sacrificing that, not to have too many weights, they had to decrease the size of the kernels. So they made it 3 by 3. This small size of kernels was because of avoiding overfitting, because of having very deep network with large kernels will increase the number of learnable parameters too much, which results in overfitting, as I said, if we don't have enough data. Okay, now let's see the network architecture of VGG. The means of the RGB images of size 2024 by 2024 by 3 were subtracted from the images as a pre-processing. Nowadays, we do that. So as you see, nowadays, we are doing the good things of all important neural networks before us. These were the history of neural networks. Nowadays, we are using the good things from them. For example, nowadays, we use that a lot. We, as a pre-processing, we subtract the mean of the images. We do that a lot. This makes the mean of the data 0. Also, most of the kernels were of size 3 by 3, a few ones were also sized 1 by 1, which means a linear transformation of features, because 1 by 1 convolution just scales that feature, right? If you have the kernel size is 1, it's multiplied that by the pixel behind it, below it, and it gives you some value in the feature map. So it's just a scaling or linear transformation. This is, by the way, if the size of the kernel is not 1, is larger than 1, then it's not a linear transformation because it's a convolution, right? Also, the stride of convolution is set to 1. For 3 by 3 convolutions, padding size is 1. Okay. Max pooling is used. They use max pooling with width 2 and a stride 2. So it's a non-overlapping pooling in contrast to AlexNet, which used overlapping pooling. In various versions of VGG, the number of convolutional layers differ. So they had several variants of VGG with different number of width depths. But this number is usually very large. After the convolutional layers, there are 3 fully connected layers, again inspired by LeNet and AlexNet. The first 2 fully connected layers have 4,096 neurons, and the last layer has 1,000 layers for classification into 1,000 classes. As we have 1,000 classes, we need 1,000 layers in the last layer. All hidden layers have ReLU activation function inspired by AlexNet. So you see, every network which came used the good things of the previous network. It used the ReLU because it was working well in AlexNet, and the last layer they used softmax inspired again by AlexNet. All versions of VGG except one of them do not use the local response normalization. See, at the time of VGG, they found out that local response normalization is not required. They dropped it. Nowadays, we also drop that. This is because they empirically found out that having this normalization does not improve the performance on the dataset of the competition. Okay, so mini batch, a stochastic gradient descent was used with momentum. We talked about all of these in the previous sessions, right? For training VGG. The batch size was 256. The batch size is usually set to a number which is a power of 2. This is not according to theory. According to practice in industry, they put it usually to the power of 2. For example, 64, 32, or here 256. The momentum parameter was set to 0.9. Usually they set it to a big number. Why? Because they want to have high momentum in VGG. They don't want to have too much oscillation. We talked about momentum also before. This is set to a number close to 1, not to have too much oscillation in training. Weight decay with L2 norm was used for regularization. Okay, so they used L2 norm weight decay for regularization. Also, by the way, we'll see weight decay, I think, in the next session. The regularization parameter of the weight decay was set to 5.5 times 10 to the power of -4. So the regularization parameter should be small. But you might be wondering, why am I saying all of these numbers to you? You don't need to memorize them. This is just their experience. You are using the experience of the monsters in this AI. So I'm telling you to increase your experience of how to use neural networks. So of course, the regularization parameter of weight decay should be small because it shouldn't overcome the impact of the actual cost. Okay, because weight decay basically means that the actual cost plus lambda, the weights, the squared L2 norm of the weights. This must be a small number because the actual cost is important to me, right? It's a very small number, not to waive the impact of the actual cost. The initial learning rate was 10 to the power of -2, a small number, right? So it shouldn't be too big to jump. It was decreased by a factor of 10. So they use adaptive learning rate because initially I need to explore with large learning rate, then gradually I'm supposed to get close to the actual solution. So at the end, I need to, I shouldn't oscillate around the actual solution. So my learning rate should decrease gradually. Every time they divided that by a factor of 10, every time the validation accuracy stopped improving. This is what they did. Note that learning rate should be small enough not to have oscillation, but not too small so there is progress in training, of course, right? And this is the figure of ImageNet. For example, as you see, we have too many layers. We have too many layers. One of the variants of it. Any question? Okay, VGG is over. The next structure is Inception and GoogleNet. Again, we are coming further in the time. Inception is a module of neural network. It's a module, okay, proposed in reference 3. So it's the same paper which proposed GoogleNet, composed of Inception modules. So they put Inception modules next to each other, they stacked them, and they named the network GoogleNet. I think it's obvious that it was proposed by Google, okay? The name of GoogleNet has two inspirations. The first inspiration is the name of Google, as it was proposed by Google employees. The second inspiration is the LeNet network, which was one of the first successful convolutional networks. Why? Because when you see GoogleNet, consider the LE at the end of the GoogleNet, it becomes GoogleNet, right? Interesting. So it has two meanings actually, Google and LeNet. So in that competition, the year of competition in 2014, GoogleNet achieved the top result and won the competition. Of course, in Google, they had a lot of GPUs, a lot of resources they could train it. There are two ways to increase the number of learnable parameters in a neural network. Do you agree? There are two ways we can increase the number of learnable parameters. Either the depth of the neural network or the number of hidden neurons can be increased, or both. What do I mean? So I want to increase the number of learnable parameters. At that time, this was the main idea of researchers. They said, in order to achieve top results in the competition, we have to have too many weights to train. So VGG increased the depth. Another way to increase the number of weights is to increase the number of neurons in the layers, right? Or we can do both. This increase in the number of learnable parameters has two drawbacks, okay? Two problems. First, it makes the network prone to overfitting, especially if there are not sufficient labeled training data, right? If we have too many parameters but not enough data to train them, we will have overfitting. And labeling data, we know that labeling data is time and resource consuming. Labeling is hard in industry. And also, if you have worked in industry, you know that you should pay people to label data for you. Second, more parameters need more training, requiring more computational resource, right? So we need more computational resource as well. For resolving these two drawbacks, the Inception module was introduced, which inserts sparsity to the network. So Google's employees said that let's insert sparsity to the network, not to have too many parameters. Although we make the network big, but we don't want to have too many parameters. This is also beneficial, as I said, as we have sparsity, according to the Bettina sparsity principle, and Occam's razor is beneficial. Okay. So it is, now I'm talking about Inception. It is possible to suppose that every neuron in the previous layer of a layer corresponds to some region of the input image. Do you agree? Every neuron captures some features of its input, right? And so, you know, it's like a neural network is like, whenever I look at the neural network, I see team working. It's like a team. It's like neurons are collaborating. Some neuron captures features from some region, and then the other neuron or the other filter kernel says, okay, you got the features of that top right region. Let me get the features of the top left region. Another filter, some other neuron says, okay, you two got the features of those two parts. Let me get the features of another part. So it's like a collaboration, right? As a result, we can say every neuron can be corresponding to some region of the input image, right? On the one hand, in the initial layers of the network, the correlated neurons concentrate in a single region. Okay, so when we have some neurons which are correlated to each other, then they concentrate usually to the same single region. As a result, many clusters of neurons concentrate in a single region. So usually many of the clustered neurons can correspond to the same region, right? These clusters for a single region can be covered by a layer of 1-by-1 convolution. Okay, note that 1-by-1 convolution can be seen as a linear transformation. I told you the reason. Okay, on the other hand, there are a smaller number of more spatially spread clusters of neurons which can be covered together by convolution on larger patches. So basically, let me recap. Sometimes some neurons which are close to each other spatially, they correspond to the same region. Sometimes some neurons which are away from each other, they correspond to the same region. For capturing the neurons which are in the same cluster spatially next to each other, we use 1-by-1 convolution. But for the ones which are a bit spatially spread clusters, then we can use convolution on larger patches. Okay, so basically that's the reason. Inception module uses 1-by-1 convolutions, also 3-by-3 convolutions, also 5-by-5 convolutions. These are the reasons. Okay, note that the larger and more spread the regions are, the less the number of the clusters is. Do you agree? If we consider the clusters to be adjacent neurons, we will have too many clusters. If there are sparse neurons forming a cluster, when the number of clusters decrease. Therefore, only small convolutional kernels are used. We don't need to use too large convolutional kernels. As a result, 1-by-1, 3-by-3, and 5-by-5 are enough. This explains why the inception module is sparse, as it does not use large convolutional kernels which are denser. Okay. Therefore, for the above explanations that I talked to you about, the inception module uses 1-by-1, 3-by-3, and 5-by-5. Okay. Moreover, because of the benefits of pooling that we talked about before, 3-by-3 max pooling was also used, because we know map pooling does downsampling, also makes it robust to local translations, etc. Right? So we have these four things. We fit the previous layer to these four things, then we concatenate them. Okay, this is called inception module. Okay, GoogleNet stacks the inception modules as its layers. Do you remember I told you, for example, several times I told you that deep leaf network is a stack of restricted Boltzmann machines, right? Also, but if we stack inception modules back to back, well, the neural network is called GoogleNet. The number of 1-by-1, 3-by-3, and 5-by-5 convolutions can change in the inception module depending on where it is used in the network. So if the inception module is in the first layers or in the last layers, then the number of these convolutions might change. In the higher layers, close to the output of the network, more abstract features are extracted. Okay, usually if I don't know if you have trained neural network or not, usually when you train that and you visualize the features extracted in the layers of the neural network, initial layers are like sine and Gabor filters. Have you seen Gabor filters? Let me show you Gabor filters. Let me share a screen again. These are called Gabor filters. Okay, these like sine and cosine. It's like exponential operator on the sine and cosine. Okay, usually the initial or like this initial layers extract something like this. These are very interesting, but the more we go in the layers, we will have more abstract features. It's very interesting. So the features become more abstract. By the way, these Gabor filters are also in our eyes. Now it's very interesting. The initial layers of the convolutional neural network extract the features like the features extracted by our eyes. That's why it's like neural network, convolutional neural network is looking at the image, because we look with the same filters to our world. It's very interesting. Okay, so as I was saying, in the higher layers close to the output of the network, more abstract features are extracted. Therefore, the larger convolutional kernels are required more in higher layers. As a result, the inception modules in the higher layers close to the output should contain more 3x3 and 5x5 convolutions compared to 1x1 convolution. Okay. However, having larger convolutional kernels results in too much computational complexity, right? Because, for example, the 5x5 convolution is applied on the result of the 5x5 convolution in the previous layer. It exponentially explodes. 5x5 applied on 5x5 is too much. Having multiple layers of these large convolutions results in computational blow up. Of course, we'll have memory error, for example. To resolve this problem, dimensionality reduction by 1x1 convolution linear transformation of features is added in the inception module. So what do I mean? Here, do you see? I have 1x1, 1x1, also here 1x1. These are for 1x1 convolution. I don't need 1x1 transformation, dimensionality reduction. But for these, I need not to have this explosion, these computational blow up. So we have this. In other words, 1x1 convolutions are added before the expensive 3x3 and 5x5 convolutions, right? To kind of cancel the result of 3x3 and 5x5 convolutions of the previous layer. So, by the way, this is the final inception module used. Okay. So this is the network structure of GoogleNet. As you see, it is using, these are inception modules. It is stacking the inception modules, right? So the means of the RGB images are subtracted from the images to have the mean 0. They were inspired by VGG, right? As I said, they use the benefits of the previous networks. GoogleNet is a stack of inception modules as its layers, and all the convolutions, including the ones within the inception modules, use the ReLU activation function inspired by AlexNet. Interesting. Okay, any question? No. The next structure, network structure, is UNet. UNet was proposed in reference for a biomedical image processing application, which was biomedical image segmentation. UNet is usually used for segmentation when you want to segment your input image, okay? Partition it into several classes. And why is it very useful for biomedical images? Consider, let me tell you, a histopathology image. Have you seen a histopathology image? Let me show you. Histopathology image. Okay, something like this, or these. Do you see them? So you can segment the cells, for example, or do you have tumorous parts? here, for example, you have tumorous parts, you have some cells, you have nucleus, and these things, you can segment them. So it's for biomedical data, it's very useful. Or if you have X-ray images, you have some parts where doctors focus more, so you can segment them. These things, so you can. It's very useful for biomedical images as well. It was winning submission for ISB challenge. By the way, ISB is one of the very important conferences in biomedical area. ISB challenge for segmentation of natural structures in electron microscopic stacks. So it won one of the competitions of the biomedical area. It is named UNet because its shape is like the letter U, like this, as you see, it's like the letter U. A UNet has a contracting path like the downward edge of the letter U. So this is contracting path because what does it contracts the image? It makes it smaller and smaller. Also an expanding path here because it makes it bigger and bigger, like the upward edge of the letter U. The contracting path is for capturing the context, and the expanding path is for precise localization. Okay, so basically this part is like capturing the context. It captures the context of the image because it's making it smaller and smaller. So the smaller it becomes, only the context remains. Then for expanding, we use it for localization and segmentation. Which parts are more important? Okay. So what does it do? The network architecture of UNet is like this. So it says the contracting path has the layers have 3x3 convolutions, okay, followed by ReLU activation functions. Again, many networks nowadays are using ReLU activation function, right? After every 2 3x3 convolution followed by ReLU activation function, they use max pooling of width 2 and stride 2 for downsampling. I think it's obvious. In the contracting path, we need to downsample further and further. For downsampling, we can use max pooling. We saw that, right? At every downsampling, the number of feature channels is doubled. So basically what they are doing, they are reducing the size of the image, but for compensating this reduction, they are increasing the number of channels. So this is reducing to this, but the number of channels is increasing to this, right? Until the number of channels become too big. And then the other way around is for the other side. So they expand the size, they upsample it, but they decrease the channel sizes. Okay. The channel size, I mean this. Do you see the width? The width, do you see them? It's becoming thicker and thicker. Here it's becoming narrower and narrower. The expansive path, as I said, the layers have 3x3 convolutions followed by ReLU activation functions. After every 2 3x, so it's like the mirror. After 3x3 convolution followed by ReLU, we have a 2x2 up convolution. This is a new thing. It's a reverse of convolution, also called transpose convolution. So for upsampling, we can use there is a technique named up convolution or reverse of convolution, or transpose convolution, different names for the same thing. I will talk to you about upsampling in the next slide. At every upsampling, the number of feature channels is halved because they are upsampling, but for compensating that upsampling, they are reducing the channels, the number of channels. After every upsampling, the result of upsampling is concatenated with the cropped output of the corresponding layer in the contracting path. So I'm talking about this part now. What do they do? At every part, at every layer, they concatenate its mirror in the contracting path with the result of the previous. So this is concatenated with this to get this. Okay. So they concatenate this. Also, cropping is required because the border pixels are removed at every convolution. I think now put yourself in the shoes of the developers. I think they coded that and they found that they get some error. They said probably there is a problem with the sizes. So they found out that after debugging, they had found out that they need to do cropping to have the same sizes. Okay. And here are the legends of the picture, by the way. Here we have convolution, up convolution, max pooling, copy and crop. Here, these are copy and crop, and 3x3 convolution with ReLU. An example of up convolution or transpose convolution. You can see this website also. Consider this image, okay? And this is the filter kernel, okay? We want to do transpose convolution. What do I mean? So this kernel times this gives me what? This. I put it here, right? Then this whole kernel times this gives me this. This whole kernel times this, I mean element-wise time multiplication, gives me this. This whole kernel times this gives me this, right? Now put them next to each other with the same order as this. So you need to sum them, by the way. You need to sum them. So I put them in the order that I had, but here, for example, I have zeros here. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Then add them up. This gives you a 3x3. So we upsampled it from 2x2 to 3x3. Did you see what I did? This is an example of upsampling. So, and as you see, it's convolving, hence the name convolution, but it's transpose convolution. UNet was primarily implemented in the CAFE library. CAFE library is one of the libraries for deep learning, but nowadays I think it's extinct. Nowadays people use either TensorFlow or PyTorch, but CAFE was one of them. And because of the large input tiles of biomedical images, the batch size was set to 1 in the unit. So as I told you, the input tiles are very big in the, especially histopathology and biomedical images. As they were too big, they set the batch size to 1 because of not getting memory error and not to become too slow in training. Similar to VGG, UNet also sets the momentum parameter to 0.9, inspired by VGG, right? To have high momentum and less amount of oscillation in training, right? The final feature map of UNet has the same size as the input image. The final feature map has C number of channels. Why do I need, by the way? Can you tell me? The final feature map of UNet has the same size as the input image. Can you tell me? I mean, the number of output neurons is the same as the number of input neurons or the number of data image. Can you tell me? This is because we are doing segmentation. We are doing classification per pixel, right? So classification per pixel means segmentation, right? So whatever pixels we have in the input, we should have in the output, because we need those number of neurons for classification. So the final feature map has C number of channels with softmax activation function, where C is the number of classes in image segmentation. Basically, what do I mean? Assume your image is, input image is 15 by 15. Assume 15 pixels by 15 pixels. And you have C number of classes. C can be 2, can be 3, whatever number of classes you have for segmentation. In the output, what do I have? I have 15 by 15 by 3 neurons. Per pixel, I have C number of channels. And I use softmax activation function for classification. Did you understand? So I have the number of outputs, the same as number of inputs, but with a C number of channels for classification per pixel. The last function of UNet is cross entropy, because we are doing classification. For classification of the pixels into one of the classes of segmentation. Did you understand? Any question? No? ResNet, the next architecture. It has been empirically observed that in very deep neural networks, for example, with more than 20 layers, okay, by increasing the depth of the network, accuracy saturates and then degrades rapidly. That's very interesting. So do you remember I told you that let's increase the number of layers? That was the dominant thought of them at that time. Let's increase it to have more number of parameters to learn, right? So let's increase it, the number of layers. They said that when we increase it, they saw that empirically. Then when we increase the depth of the network, accuracy increases, but after some level, it saturates. And when you increase further, it suddenly degrades. It goes down, accuracy goes down rapidly. In other words, by adding more layers to very deep neural networks, the training error increases. This problem is referred to as the degradation problem. Okay? The degradation problem is surprising. This is because a neural network with additional layers is a special case of the shallower network. Do you agree? When you have, for example, assume you have a neural network with 5 layers and it works very well. When you increase it to 10 layers, if the 5 layers were good enough, then the backpropagation should find out that 5 layers are enough and then sets the 5 other layers to be identity mapping. Why doesn't it do that? Because 5 layers is a special case of 10 layers, where 5 layers are can be identity map. But surprisingly, in practice, they found out no, apparently it's not like that. In practice, we have the degradation problem. So in other words, if the shallow network is sufficient for learning, the additional layers are supposed to become identical mapping by optimization in backpropagation. However, this problem surprisingly exists. ResNet, short for residual network, was proposed in reference 5, which uses deep residual learning for resolving the degradation problem. So ResNet was proposed for handling this problem. What does it do? In the regular networks, it is hoped that each few stacked layers directly fit a desired underlying mapping. Okay, in regular networks, it is hoped that we can each few stacked layers, several layers, directly fit a desired underlying mapping, right? We can learn some mapping. In the deep residual learning, however, each few stacked layers fit a residual mapping rather than direct mapping. I will tell you what it means. Okay, so residual mapping versus direct mapping. Let the desired original underlying mapping which you want to learn be denoted by h of x, where for the input x, right, to the stacked layers. So x is the input to the stacked layers. In that deep residual learning, the stacked nonlinear layers fit another mapping. So they fit this. Rather than fitting h of x, they fit h of x minus x. We denote it by f of x, okay? This is residual mapping. What does it do? Therefore, the desired original mapping now restate this, rearrange the terms. So h of x, which was the original mapping, becomes f of x plus x. Now let's illustrate this equation for how is it? So we have x as input to the stack. Then we have some layers, for example, 2 layers here, ReLU activation function between them, right? Then here I have f of x. So f of x models this. And also I have a copy of x. I bring it here. Then I add, so according to this, I add them, f of x and x to each other. So it gives me f of x and x, and then I feed it to the ReLU activation function, right? So basically, before ReLU activation functions, f of x plus x is the h of x. This is what ResNet does. As I told you, this is a rearrangement of equation 3. Okay, and this is residual, right? Residual error. Benefit of ResNet. In backpropagation, gradient can flow directly through the identity function from the next layers to the previous layers. So what is the benefit? Can you tell me? In regular neural network, we don't have this, right? We don't have this additional identity adding. If we don't do that, then in backpropagation, the error goes like this, goes back like this in the chain rule, right? But this might result in gradient vanishing or gradient explosion, because I have too many layers and they are multiplied by each other. So if I have too small numbers, gradients, I will have gradient vanishing. If I have multiplication of too large gradients, I will have gradient explosion. But when I have this part in backpropagation, I have some other path too to go through. So in addition to this path, I have this path too. As a result, I bypass some of the multiplications. Therefore, I will not face gradient vanishing or gradient explosion. It's interesting. The deep residual learning postulates that conjectures that it is easier to optimize the residual mapping than to optimize the desired original mapping. It's easier to map f of x rather than h of x, which is unreferenced. Empirically, this postulation has been approved to be correct. So by experiments, they showed that this postulation is correct. As you see, this is the ResNet. Variants of, we have variants of ResNet. So we have ResNet 18, ResNet 34, ResNet 50, ResNet 101. So these means how many layers they have. The more the number of ResNet, so the larger it is. Usually in our PCs, laptops, we can run ResNet 18. For ResNet 34 above, you need servers. Don't run ResNet 34 or ResNet 50 on your computer. You might lose your computer. It might become so much hot, and you might break down your computer, or you might get memory error. Okay. Choose based on your computer, memory, CPU, application, and data. So comparison of architectures of regular net, VGG, and ResNet. Take a look at this. So this is VGG. This is regular neural network, convolutional neural network. This is ResNet. As you see in ResNet, we have these bypasses, right? And we have a stack of them. We have a stack of ResNet modules. And how many of these do we stack? For example, if 18 stacks, we have ResNet 18. If 34, we have ResNet 34. Okay, I think we don't have enough time to go through other architectures. In the next session, we'll cover DenseNet and let me see what else. Yeah, DenseNet. And then afterwards, we'll go and cover regularization and regularization in machine learning and deep learning. And afterwards, we'll go to recurrent neural networks and LSTM, and then attention mechanism and transformers and GPT and BERT. Any question? Any question, guys? Can you hear me?
Hello.
Yeah, no question. Thank you.
Yeah, no problem. Thank you. What is the question?
I want to ask that how do we choose the number of neurons and layers in the CNN?
How the number of what?
Neuron and layer. How do
Okay.
we choose
The number of
neurons?
yeah. So the number of neurons and the number of layers, these are hyperparameters. So you can by trial and error, you can see how it works. But I can say that for what do you do for tuning hyperparameters in machine learning? Do you remember? Assume your machine learning algorithm has some hyperparameters. Any machine learning algorithm has some hyperparameters. SVM has, PCA has, neural network has. The hyperparameters of neural networks are like batch size, learning rate, the number of neurons, the number of layers, right? The number of fully connected layers, the number of convolutional layers. you can tune them by validation.
Validation. Yes,
Yeah,
I know that.
you shouldn't tune them by test. It's cheating. You shouldn't tune them by train. It's bad for you because you will not find out overfitting. You should tune them by validation.
Yes, I know that I should tune them by validation, but at first I think uh, is there anything to do with the image data or the data we are using as input?
As
Like,
I mean, you mean as in pre-processing?
so if you could show some example that like for this kind of data, input data, you have to use such amount of neuron or layers. Like, is there anything like that? Or
Yeah,
it's totally dependent on the validation?
so for I'm saying that usually we try, for example, we have an image data. Okay,
Yeah,
assume we are in industry. Okay, so
yeah,
in project, I'm gonna ask you to try different neural networks and see which one is and analyze them, compare them. But I'm
okay,
talking about industry now. Industry. Usually ResNet works very well. So the first thing I think you can try, but easier than ResNet is simple convolutional neural network or the simple, which has several convolution layers followed by some linear dense layers. Okay, so if you want to do a fast trying, try a simple convolutional layer, maybe with 3 to 4 convolutional layers and maybe 2 layers of fully connected. So I'm saying this by experience, okay? And
okay.
usually it
And the
works
number
well.
of neurons?
The number of neurons, it depends on your size of your input data.
Okay.
So
Such as?
sometimes if your input data is very big, for example, the histopathology images that I showed you, they are
Yeah,
very big. So they patch them. So you can patch your data into several patches. But if they are not too big, then they are good enough to use them as they are. And then you feed them. Then you choose the sizes of neurons in the layers in a way that you gradually decrease. So you shouldn't, by experience, I'm telling you that you shouldn't decrease rapidly. For example,
okay,
if in this layer you have 1,000 neurons, you shouldn't suddenly make it 100. Make it
okay.
gradually. Make it 800, then 600, then 300, then 100. Do you see that?
Oh, yeah,
So do it gradually, and by this graduation, you also we will have several layers. Don't have too many layers. Otherwise, remember that by
overfit.
increasing the number of layers, you're increasing the number of weights. You need more data to train, right?
Okay,
And also, you shouldn't be too shallow because we are not in 1990s. We have resources. So you should somewhere between, for example, maybe 5 layers, 6 layers, 7 layers are good. Do you
okay.
get it? And
Yeah,
you're decreasing it gradually. And in industry, so CNN worked well, then let's try ResNet, see how it works.
okay.
Usually ResNet also works well.
Thank you so much.
No
At
problem.
first, at the beginning, you told that why do we use the fully connected layer at the end?
At the end, because
Yeah,
if at least in the very last layer, I have to use fully connected layer. Otherwise, for example, I have image data and I have
yeah,
5 classes. Then if you don't use any fully connected layer, how do you have 5 neurons at the end for doing cross validation on them? Sorry, cross entropy on them. So because you need
okay,
5 neurons at the end with softmax activation function, right?
yeah,
So at least you have to have one fully connected layer at the end to map their feature maps to
yeah.
5 neurons,
5
right?
neurons. Okay, yeah, got it.
But
Thank you.
usually we use several fully connected layers, not just one. At least by convention, by experiments, we are following the monsters. The monsters, like in AlexNet, in ResNet, they are usually using several fully connected layers at the end, and they saw that it's working well. Google has seen, Facebook has seen that these are working well, so we follow them. Do you see that?
Yeah, thank you so much.
No problem. Any other question? No? Is everything clear now? Okay, guys. Thank you very much. As I said, again, next session will be in person. My car got fixed. From the next session, it will be in person. For the statistical machine learning, I will also email and say that will also be in person. The exam will also be in person. So everyone is supposed to be present in person in the midterm exam as well. Thank you very much. And I have posted the assignment solution as well. And if you have any question or ambiguity, feel free to ask me in the Teams and tag me. Okay, thank you. Have a good night. Bye.